All right, perfect. So someone remind me, what were a couple of the things we covered towards the end of class on Thursday last time? So we definitely did stuff about limits, but what specifically? We did left hand limit and then the right hand limit. In particular, we talked about this one particular theorem. Someone remind me, what was that theorem stating that related the left hand, the right hand limit versus the two hand? Yeah, so that theorem that we talked about last time stated if the left hand limit, I'm just going to rewrite it. Y'all already wrote this down, but just as a reminder, again, this is what we covered last time, or what we ended with. Our theorem from last time stated the limit as x approached c from the left is equal to the limit as x approached c from the right was equal to L. Ran out of room here, but because I wrote really large. This occurs if and only if the limit from the left and right of my function is also L. So in other words, my left hand and the right hand limit are equal if and only if the two-handed limit is also the same value. The other way that we could have interpreted this was if I know what my left and right hand limits are, I know what my two-handed limit is. If I know my two-handed limit, I have an idea about my left and right. In other words, either all three of these quantities matched or all three of these quantities were different. What was my two-handed limit if my left and right were different values? What did I say my two-handed limit was? Does not exist. We didn't really do a proof for this one because it's a little bit more into the definition. The definition of our two-handed limit was looking from the left and the right. Exactly what we have here, the left and the right. All right, so we talked a little bit about the left hand limit and the right hand limit. Today we're going to take sort of a slight tangent away from that. We'll come back to it probably tomorrow. So first thing I'll mention about the content we do for today. And if you have a friend that happens to not be here today, today is not a good day to miss because we're going to be doing some mathematical notation and our first very formal proof. So let's go ahead and talk about some common mathematical symbols. Like I said, we're going to be doing some proof-based mathematics today, a little bit of theory. But to do some theory, we need to understand what do a couple of these symbols mean for us. So a lot of these symbols is likely that, depending on your background, you haven't seen it. Usually students for Cal 1, this is their first time ever seeing it. This symbol looks like an upside down A. This is notation for all. So we have our first notation. Additionally, I'm going to use, it looks like a backwards E, meaning there exist. So if you ever see this upside down A, it means for all. Backwards E, it means there exist. Let me write this notation. Oops, let me rewrite that. Not A, but little a. This notation, this is saying A belongs to the set B. A being A, B being B. This little symbol between the A and B represents it belongs to the set B. And there's about 9 symbols I'm going to show. Some of them are familiar. Some of them, obviously, these not as familiar. Does anyone know what the symbol for real numbers is? For all real numbers? It was an R. Was there anything special about the R? Yeah, it had two little lines along it. So that's going to be my next common symbol. Let me zoom out on this so that everyone has it. So if you ever see me write this here, let me make this a little bit smaller. It looks like I just did an R with another line on it. This is the set of real numbers. I'm being a little bit lazy and write just numbers. As I mentioned in this class, we're primarily dealing with the real numbers. We're not going to be really talking about imaginary numbers. So real numbers, essentially any number that we're going to be using in this class, any number that you typically think of. So nothing about I, square root of a negative, anything like that. So also just tying back into this, again, don't write this part. Someone tell me, what does it mean here, and then, if I write that? Yeah, so x belongs to a set of real numbers, or more casually, x is a real number. So this is me saying I have an x, it's a real number. So this is combining some of our notations. All right, moving up from here, let's see. Do I want to introduce all the notations? Probably not. This one is not going to have an exact meaning, but whenever you see me write this, it's going to represent an epsilon for us. And then this will represent a delta. Some books write it more like this, where it's a flat line. Same thing, is a little bit how you prefer to write it. So an epsilon and a delta. So now we have some notation that we're going to use for today. Clearly, there's much more notation theoretically, but these are the ones that we're going to be referring to for the most part. So at the our first lecture class, I talked about the definition of the limit. I gave you a definition, and it used words such as sufficiently close, close enough, arbitrarily close. But then those terms were very ambiguous. We would ask the question, what does it mean to be sufficiently close? What's close enough? So mathematicians went ahead and said, let's go ahead and define what does it mean to be close enough. So what we're going to do is we're actually going to go ahead and reintroduce the definition of the limit, but we're going to call it the precise or formal definition. Or the other term that you often see in math is called the Epsilon-Delta definition of the limit. So the Epsilon-Delta definition of the limit. All right, so what I'm going to do is I'm going to write a little bit of a briefer version. So we can write that the limit as x approaches c of f of x is equal to L if the following property holds. So I'm allowed to use our notation that we are accustomed to. I can say it's equal to some value, provided that this property I'm going to write here holds true in all cases, or in the conditions we've defined. So hopefully you've written down those that notation with the Greek letters and the for all and everything, because I'm going to write it using mathematical shorthand, and then we're going to read to see what does that mean. So it's going to look like I'm going to be drawing a bunch of symbols because I will be doing symbols. So this is the start of it. Someone read to me this based on that notation we just introduced. All right, let's start one by one. Read the first set of parentheses. Left hand, greater than 0. So the first off, for all epsilon greater than 0. Second part, a little out of sync, but yes, there exists a delta greater than 0. Yes, for all x belonging to a set of real numbers, or more quickly, for all real numbers x. So this is not the definition. We haven't said anything. This was just saying we have 3 variables, epsilon, delta, x. So 3 things. So we said for all epsilon greater than 0, there exists a delta greater than 0, such that for all x that belong to the set of real numbers, we have, let's see, usually I would write it right here. Let me zoom out so I can write this. There we go. That should be sufficient. So we can say that when x minus c, the absolute value, is smaller than delta, then f of x minus L is less than epsilon. So let's interpret this. I'm going to give you all a moment to write this, panic a little bit, and then take it in. So this is one parenthesis. So this is going to be what we just said. So for all epsilon greater than 0, there exists a delta greater than 0, such that for all real numbers x, this will occur. So let's break it down piece by piece to see what does each of this mean. So I just said a whole paragraph written into a single line. We know what C is. Oh, did I forget to put C in here? Oh yeah, from C from the beginning. So if I take the distance between x and c, again, this is the x and c we have from our limit. If these are close enough, this is what x minus c smaller than delta. They're within some delta distance. We're going to figure that out. So the problem here is that, let me hold that question. Let me go through this and we'll talk about it. If this occurs, then f of x minus L, so my f of x, my function, and my limit are also really close to each other. So this is using that same definition we used earlier, but in mathematical notation. If x and c are sufficiently close, then f of x and my limit are also sufficiently close to each other. So the question here is, well, besides what are all of these symbols, what is epsilon, delta, and all of this? This is saying that if my function and the limit I want are within some distance, I can always find a delta. So for all epsilon, I can find a delta. That's why we use the word there exists a delta, such that my x and c are sufficiently close. So let's draw a picture of this and see what does this really mean for us. Let's see. Does anyone still need to copy this down? Yeah, go ahead and copy that down. So what I have here is sort of an introduction to mathematical shorthand notation. Instead of writing that entire paragraph, it's been condensed down to what we see here as a single line. Generally, for example, whenever I'm working with my math majors in their 300 level course, we might write a line that looks like this for our scratch work. And then we translate it into a paragraph whenever we actually do our work and everything. All right, so let me move this up. I'm going to draw a graph, just generically. It's a really thick line. It's drawing some random graph. Let me put a little bit more of a turn into it. All right, so here we have a function. Let's say that this right here, let's say that this is 5, and then this is 1 right here. What would you say the limit as x approaches 5 of the function is, based off this picture? Yeah, it would be 1. Again, I see here's x equal to 5. If I get closer from the left, what y value am I approaching? Same thing from the right. Kind of like what we did on that first or second lecture. So this is what we're used to. So how does this correlate to that epsilon-delta definition that I had earlier? So it started off with defining an epsilon. Remember, it had something like whenever we have f of x minus L is less than epsilon, we have the limit here 1. So whenever I'm within a certain epsilon distance, whatever epsilon might be, so 1 minus epsilon, 1 plus epsilon. Let's see what happens whenever I draw some dotted lines across. Let's use blue here. So this is 1 plus epsilon, 1 minus epsilon. Epsilon is just some small value. Our definition says I can always find a delta within here. 5 minus delta, 5 plus delta. Such that I'm contained essentially within a small box. So if I draw the lines here for 5 minus delta, would you agree that I can keep on making this box smaller until I am essentially at my limit? So this is what that definition is technically saying. I can make my box smaller and smaller until I'm actually at my limit value. So I can make this smaller and this smaller as well, and eventually I'll reach exactly that point. Now, I am leaving out a lot of details because we're not going to go super deep into this picture. What is delta? Delta is some arbitrarily small number. It's going to be based off of what epsilon is going to be. Yeah, so is epsilon the limit of whatever we're looking for? Is epsilon the number that is of x approaching? What is epsilon? Epsilon is some distance that we're allowing between my function and the actual limit. So it's a distance from here to here, in other words. So I'm going to have you hold on your question, because I know it's a very confusing thing. This picture is not going to be the point of what we're going to be doing today, but this is the visual representation. What we're going to be doing is actually proving that a limit is equal to a certain value. So I'm going to write down a limit. You're going to tell me what that limit is. What is this limit equal to based on how we've been doing it for the past week? 3. We got that pretty quickly because we do a calculation. So usually I would say, here's this, give me what it's evaluated from. Now, what if I change it up and say this? Prove this is true. A calculation is not a proof, though, necessarily. We're not even going to do a graph. We're going to use that definition I had earlier. So let's identify the things we do know. What's my C value? I'm going to do a lot of scratch work for here. Let me use red. C is equal to 2. What's my function? X plus 1. What's my L value? 3. All right, so let's try putting all 3 of those letters, well, not letters, C, L, and f of x into my definition as needed. So I'm going to start off by writing the general definition and then what this means for us. So just again, this says for all epsilon greater than 0, there exists delta greater than 0 for all x being real. No. This is kind of like the reason that we're going to be doing this is that it's going to actually technically provide the real background where all this limit stuff comes from. I'm not going to be saying something like, now pop out this definition for me without anything else. Is that the true definition of the limit? And all of calculus is going to be based on what is the limit. So everything, if you already took calculus before or you heard some words, derivatives, we're going to use the definition of a limit to define a derivative. And then almost all of Cal 1 for us up until probably this second to last week of the semester, we're going to be doing all derivatives and applications. All right, what was it? X minus C is less than delta implies f of x minus L is less than epsilon. All right, so in particular, we're going to focus on this part here, because that's the part that's the actual definition portion. Those first 3 parentheses were just, I have 3 variables. So let me rewrite this. What was C again? 2. So we have x minus 2 is less than delta. Somehow, I want to end up with, what's f of x again? What's L? Somehow, we want to prove this occurs. If I have this, eventually I end up here by defining a certain delta. I'm not defining epsilon because it says for every epsilon. We don't need to define epsilon because it says this should work for all epsilon. One of the parts that's difficult about this is that to do this problem, we're actually going to work a little bit backwards before we actually put it together our final problem. So everything we're doing right now is scratch work before we write out everything. So again, I start off here. Somehow, I say delta is this and end up here. So this is where I'm going to say we're going to try to go a little bit backwards because we know that this is my end goal. So if I'm working backwards, let's look at this. Can I clean this up a little bit? We have this because 1 minus 3, we got minus 2, right? So I still have this. What should delta be to make this true? To make this look like this? What should delta be? If I want this to be also epsilon, let's just say delta is my epsilon. What would you say delta would be if this was somehow 5 epsilon? Let's say that somehow this was 5. If I want these to match, well, 5 delta. Let me reword this. Let me hold off on that question for now. But let's see what happens whenever I do this. Let delta be epsilon. In other words, let me set these 2 Greek letters to be the same thing. So now on this side, I can write up here. Let's write this proof. Let's let delta be the same as epsilon. And suppose we do have, was x minus 2 was less than delta. It's an ugly delta. Then what? Well, what can I say about x minus 2? Again, we have that it's less than delta. What's delta again? So we have, this is less than delta. That's a given. That's epsilon. We have this so far. I did go slightly out of order for this, but that's fine. Then, remember I wanted this to be my end goal. So I'm just going to rewrite that. X plus 1 minus 3. This is still x minus 2. What's x minus 2 smaller than? It's less than epsilon. So in other words, I started off with this, and I proved that this was always smaller than epsilon. In other words, if I choose my limit and my function to be within some distance, I can always use that same value for distance between x and my c value. So going back here, I can use the same distance here. Oops, that's not right. This is the same distance as this. In other words, I have a box, a square box in particular that's shrinking to my limit point.
So is it just saying that the distance between like 5 and then like the distance between like 1, like the epsilon and the delta are the same?
Yes. So basically, whatever this was, that's the same as whatever this was here. All right, so I'm going to take a pause here. We ended up with the final result saying if this occurs, then this is less than epsilon, which was the end goal. Anyone remember what symbol did I use at the end of a proof? Yeah, we had a little box. There's also another symbol that I use sometimes, QED. Does anyone remember what did that stand for? It was definitely something in Latin. It's not something you need to know for a test. I'm seeing as a general question. Essentially, yeah. What we wanted to show has been shown, or what we wanted to prove has been proven. Remember, this was just something that I said was, I believe it was Latin for caude erat demonstrum, something like that. Probably saying that, pronouncing that completely wrong. Right here, depending on the book, the reason I'm showing you both is that some books use the line, the box here, or some books use a QED. They mean the same thing. I just want to show so that you don't see QED like, what is that? It means the same thing. You just put an empty box. That's fine. But brings up a good question. Talking about this for y'all's work. Question: will I be making you prove this on an exam? Most certainly not. This is just foundational material for theoretical background. So this is me. Unfortunately, for my Calculus 1 honors course, they will have to prove these from scratch, given something like this. But for general calculus, this goes a little bit beyond what we're used to for looking at calculus, especially considering that many of y'all came from algebra and stuff like that. So this was just a little bit of a background foundational theory a little bit of an idea about what mathematicians do for research in the background. So some of my research involves some stuff like this, proving stuff, stating a theorem, everything along the way there. All right, so before I move on, any questions about this general epsilon-delta definition? I will say I will not give this to you as the definition or anything like that as like a problem on the exam, but perhaps I might give it something as an extra bonus somewhere along the way if you can state the complete definition of the limit. Seeing how good your memory skills are. All right, so now that we've covered the precise definition of the limit, let's go back to what we were used to calculating limits. We talked about the left-hand limit and the right-hand limit. And I believe we did a couple of examples. Just remind me, did we work with, I called it an infinite limit? Does that bring any words? Where we did the limit and it was equal to infinity? Okay, perfect. Just making sure that we're on the same page there. Let me see. Let me check one thing. We're actually a little bit ahead of schedule than where I was planning for. We'll end class there because I don't want to go into a whole new section with that material. All right, so last reminder, when is that homework due? Tomorrow. I don't remember the exact time, but I thought it was 4 o'clock, but someone said 3. 5. Whatever it says on Blackboard. Yes. So the homework is an online homework where you just submit it online. One note about the homework as well. It updates as you turn it in. You do not have to complete all your homework in one go. You can do like 3 problems, grab lunch, come back. Sometimes it takes a while for it to update. So just because, let's say it says 3 out of 10 on Blackboard, but you're like, oh, I finished it, give it some time. Blackboard refreshes like once a day or once every hour. I don't remember. It takes a while for Blackboard to synchronize with the grade book. All right, besides that, I'll see y'all tomorrow.